Hello, my name is Neil. I am a postdoctoral researcher in Weizmann Institute. I want to thank you guys for coming to our show and tell sessions, in which I will do the tell part. It's about a system entitled MAJoRCom, which implements both radar and communications by utilizing index modulation. This hardware demonstration is the output of a set of joint works between the group of Yonina Eldar from Weizmann Institute and Yimin Liu and Tian Wang from Tsinghua University. The software part was carried out mostly by Jidong and Yu, who are Tian's students, and the hardware part was carried out mostly by our very own RF wizards, Yariv Shavit and Moshe Namer. Now, this demonstration is about a system implementing both radar and communications. The motivation for having a system implementing both stems mostly from two reasons. The first is the congestion of the wireless spectrum, which motivates us to explore spectrum bands typically related with radar applications for communications purpose. In addition, emerging technologies such as autonomous vehicles implement both sensing using radar in parallel with digital communications. For example, this autonomous vehicle both has to sense its environment to detect obstacles, and simultaneously it has to communicate with neighboring autonomous vehicles and road infrastructure. Now, the radar targets and communication receivers operate at similar ranges, which motivates the joint design. It indicates that by designing those functionalities jointly as a dual function radar communication system, one can benefit from, for example, size and weight reduction, have it more flexible, facilitate the coexistence of those sub-functionalities, reduce the spectral congestion, and many other possible gains. Now, dual function systems have been the focus of considerable research interest over the recent years, and there have been several leading design approaches in the literature. The first is to utilize separate coordinated signals, namely to have a dedicated communication signal, have a dedicated radar beam, transmit them both, and design them such that they will not interfere with one another, either by beam steering or by orthogonalization, either in time domain or in the frequency domain. Alternatively, one can just transmit a communication signal and utilize the echoes recovered from that communication signal for sensing. For example, it has been shown that OFDM signals have relatively good sensing capabilities, which are not that different from those of radar signals. Alternatively, one can design new dedicated waveforms, which are capable of implement both sensing and communication reliably. Our focus here is about using only radar waveforms and embedding the information, the digital message, into the radar waveform. How can you do that? Well, the rationale here is to embed the bits in the waveform parameters. For example, we have here this autonomous vehicle, which let's say wants to scan, to sense in the forward direction, and so for that purpose, it transmits a radar beam. But let's say it also wishes to communicate with this infrastructure unit. So if it wants to convey the message 101, it will transmit a waveform with some set of parameters. And if it wants to transmit 011, it will simply transmit a waveform with a different set of parameters. Now, encapsulating information in signal parameters, that's exactly what's called index modulation. And this is the concept upon which we'll build upon in our proposed demo. Now, doing such has several benefits. First, it uses conventional radar signals, making it both reliable for sensing and can utilize existing radar hardware, like autonomous radar. It also comes, therefore, at the cost of very slow or even minimal radar degradation due to the need to convey digital messages. It has its drawbacks. It has a very limited bit rate compared to using dedicated communication signals. Decoding is quite challenging. I welcome you guys to attend our talk. I will present it later on. The related talks in ICAST. I welcome you guys where we discuss the decoding of such schemes. What we do here, we demonstrate the feasibility of this concept via hardware demonstration. I will begin a bit with the theory of these such joint radar communication schemes. It builds upon index modulation. And index modulation is a relatively established context in the communication literature in which additional bits are conveyed not via constellation signals, but as addition, but in the transmission parameters. For example, in which subcarriers are transmitted in OFDM signals, in which antennas are utilized for transmission. And by doing so, one can get relatively high energy efficiency, and it all can also boost spectral efficiency. And these are the main motivations for utilizing index modulation, at least in the communication literature. Here, we will show that it can be used to realize a feasible and reliable joint radar communication system. We will build upon a specific radar scheme, which is what's called carrier-egal phased array radar. And this radar scheme wants to utilize narrowband radar signals for purposes such as hardware purposes, but it does so by randomly permuting narrowband signals among its antenna elements. For example, in the first pulse, each antenna can transmit its own specific narrowband signal, and as at each pulses, those signals change. So we have at each pulse different frequencies are transmitted, and their allocation among the antenna elements also varies among pulses. This induces what's called frequency agility, because different frequencies are utilized at each time instance, which is known to facilitate coexistence in congested environments. It also induces what's called spatial agility, in which the antennas change over time. Each antenna utilizes different frequencies over time. And it can be shown that such spatial agility improves angular resolution. What do we mean by it improving angular resolution? It means that ergodically, when you look at the horizon of a large number of pulses, it effectively uses the complete spectrum and the complete set of antennas. This means that if, for example, the instantaneous beam pattern has relatively high side lobes, because we're using a small set of frequencies and only transmitted from a small set of antennas, we're not using the complete array of antennas. Or when we're doing looking at the expected beam pattern on the horizon of a large number of pulses, we're actually getting a very directed beam pattern with low side lobes, which is quite similar to that what we would have received had we used the full spectrum and all the antennas simultaneously. Now, this inherent randomness, which is induced by the need to change the frequencies and their allocation among the antennas, is exploited in our hardware prototype to convey information via index modulation. And this is exactly what we do. We embed the digital bits in the selection of the frequencies and how they are allocated among the antenna elements. This is what's called MAJoRCom Multi-Carrier Agile Joint Radar Communication Scheme. And it's a relatively spectral efficient scheme. Its achievable rate is comparable to utilizing antennas only for communications, neglecting all the aspects of cross interference between radar and communications. Here we implement both radar and communications without any cross interference between those two schemes, which are without degrading the radar performance, simply by utilizing its inherent randomness to convey information in the form of index modulation. Now, what we're going to show here in this show and tell session is how we implement it. And we actually have implemented it using over-the-air signals. We have built a dedicated hardware prototype which utilizes an antenna with 16 antenna elements to transmit the joint waveforms over the air. Now, in order to generate radar targets, we use what's called a radar echo generator. And this radar echo generator, it receives the waveforms which propagate through the channel. Then it generates targets with controllable velocity and range, and the echoes are then transmitted over the air and received by the antenna elements. The overall prototype looks like this. It is controlled by the GUI application, which controls the parameters of the simulation. The joint radar communication waveform is generated by this FPGA, which converts and generates signals in analog and forwards them to be transmitted by the 16 elements transmit and receive antenna, which is divided for 8 elements for transmission and 8 elements for receive. The waveform which propagates through the channel is received both by the radar echo generator using its antennas and by a dedicated antenna connected to a receiver, simulating the communication receiver. The data received from the communication receiver is forwarded to the application. The radar echo generator generates echoes, transmits them over the air. They are captured by the remaining 8 antenna elements and forwarded back through the receiver FPGA to the application to process both the communication the received signal and the radar echoes. Now, this concludes the tell part of this show and tell session, and now we will go into the show. But before we do that, I just want to first recommend you guys to look into our papers in arXiv. This first paper here is about the radar scheme. This one is about its extension into a joint radar and communication scheme. I would also like to encourage you guys to join our presentations in ICAST. This first presentation takes place at Tuesday morning. It will be given by Tian. It's about the radar part of the scheme. The second presentation, which will be given by me on Thursday morning, will be about its implementation as a joint radar and communication scheme. So I hope you enjoy the show part, and be sure to check us both on arXiv and our presentation. Thank you very much.
What you see in here are actually the transmitter based off the Xilinx FPGA and 16 transmit channels which we are using are going directly to the phased array antenna, of which we are using 8 antenna elements in the upper part. We are transmitting pulses which are being collected by 2 antennas. We refer to the green antenna, the communication antenna, and to the red small antennas as a receiving and a transmitting. Those 2 patch antennas here are for the radar echo generator. One antenna serves as a receiver. It receives the 32 pulses, converts them into baseband over the baseband channel in the back of those devices in the spectrum analyzer, and then diverts it to the signal generator, which has also fading capabilities. Those fading capabilities are made easy to simulate exact echoes, which are then over this antenna go back to the receiver part. The other mode of this receiving antenna is also to send directly via coaxial to one of the receiver channels. And via baseband, we are taking them for post-process into the laptop.